Got it. Okay, so we have 3 sections to cover in the next 2 days. So our first section is on the chain rule. So a little bit of motivation. So I covered a video on derivatives of trig functions. The derivative of tangent is secant squared. And then if we're going to do the second derivative of that, we don't have a way to deal with the squared function and then secant being inside the squared function. So we split it up into the product, secant times secant, and then we do our product rule. So I worked that out ahead last night. So we end up with 2 secant squared tangent x as our second derivative. So it is possible to work like this. Now, let's talk about the chain rule. So we got 2 different expressions here. F of x smushed onto g of x, and then f open parentheses g of x. So what's different between these two? Yep. So the first one, they're being multiplied. The second one, they're being composed together. One inside the other. So we have a product rule for doing the derivative of products. But right now, we're going to learn about the rule for composition. Turns out the rule actually isn't that bad, and it's going to save us work, like we just saw with the second derivative of tangent. Like that was a function composition that we had to work differently, but if we can deal with the composition, then it works out nicely. So it turns out that when you have a function composition, the derivative ends up being the derivative of the outside function with the inside function kept the same, and then times the derivative of the inside function. And then the chain rule can actually chain again and chain again. So if you have a lot of function and function and function and function, you can get a lot of these chains on the end of derivative of the inside, derivative of the inside. So this takes some practice getting used to it. Another way to think of the derivative is when you have an outside and an inside function, you can call the inside function u. I like to call it u for ugly. So you write the outside function in terms of u, and then you multiply by the derivative of u in terms of x. So like either of these forms will work for doing the derivative, but the second form here is extremely useful when we do this, when we undo the chain rule. We're going to get a lot of integrals where if we can see that it was a chain rule setup, then we can undo the derivative a lot easier. So we're going to try it both ways. All right, so when we look at this one, we have y equals the quantity 5x squared minus 5x minus 6, all raised to the 11th. Now, without the chain rule, we would have to break this apart as an 11-piece product, which gets real tedious. But with the chain rule, so when we look at a function, we want to focus on what's the outside and what's the inside. The good news is a lot of times the inside is inside parentheses. So here our inside parentheses is that 5x squared minus 5x minus 6. So if we're using that u definition, that's our u. And then y would become u to the 11th. So if we're going to take our derivative of y, let me just go with this. So what's the derivative of something to the 11th power? How do we do that derivative? Yep. We bring the power down as a constant. So 11 times u, and then 11 minus 1 is 10. Now over here on our u, we're going to do our derivative. So we have 5x squared, so that'll be 5 times 2x, and then minus 5 times 1x to the 0, which is really just minus 5. And then the derivative of a constant is 0. So if we clean up our u prime, we get 10x minus 5. So then our final derivative our derivative of y with respect to x is dy du, which is what we found first with the y prime, times du dx. And that's what we found when we took the derivative of u with respect to x. So we have 11 u to the 10th, but I'm going to fill u back in. So that was 5x squared minus 5x minus 6. And then it's times u prime, which was 10x minus 5. So this form in here where we have dy dx is the same as dy du times du dx. So that's the way we read them, but you can, like, they look like fractions and it looks like the du's cancel out and we're left with dy dx. That is what's happening. We can actually think of these as separate pieces in a fraction that we can actually manipulate. We don't do that initially at first when we're learning about derivatives because we want you guys to think of the derivative with what you're taking it in respect to, like to be together as an operand, but they can kind of be separated. So we ended up with 11 thing to the 10th times the derivative of thing. Now, you don't have to go through all the writing dy, du, du, dx, like splitting it all out like this. But I find the first couple times when you're doing the chain rule, that can help. But after a while, what happens is you look at your function and you're like, okay, there's my inside, there's my outside. So let me focus on the outside. Outside is a power rule. So I'll have 11 thing to the 10th times derivative of my inside would now be 5 times 2 is 10x minus 5. So we get the same result without having to write so much. But you want to get used to the way the pieces are interacting, how it all works. So what questions do you guys have on this first example of the chain rule? So when we say dy du, that's saying take the derivative of y with respect to u. And that's because I wrote y in terms of u. So when I did my y prime and I just treated u as a variable like it was an x, then I was taking the derivative with respect to u. So I got the 11u to the 10th. Then du dx was taking my u, which was defined in terms of x, and taking the derivative with respect to x. So I'm treating x as my variable of focus. So when we multiply the two of them, the du's cancel and we end up with dy dx, which is what we actually wanted to find. So I took my dy du piece, the 11u to the 10th, that's the green, but I filled in u, times my du dx was the 10x minus 5. But our differential form here, that was the alternate definition of the chain rule. Like right here. Now, did that answer your question or no? All right, so let's go back to our tangent derivative. So our first derivative is just recalling the derivative of the trig function. So I looked at the test and it looks like we're not going to give you the derivative of the trig function. So you are going to have to remember the derivative of the trig functions. So like sine, derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is secant squared. So there's our first derivative. And then our derivative of secant is secant tangent. All right, so looking at our first derivative here, and we want to take the second derivative. So secant squared x, that is a shorthand for secant of x squared. So there's our parentheses with our inside versus our outside. So the outside function is a thing squared. The inside function is secant. So now when I go to treat this as a chain rule, I'm going to do my power rule on the outside. So it'll be 2 thing to the first power, and we keep thing the same, secant x. And then we're going to multiply by the derivative of the inside, which the derivative of secant is secant tangent. And then if I clean this up a little, I end up with 2 secant squared tangent. Which is the same derivative I got at the front when I did the derivative using the product rule. But this is less work than doing the product rule. But it takes practice being able to see the function composition, to see what's the outside function, what's the inside function. So a lot of your homework, like before this next test, is just practicing doing different derivatives in different scenarios. So much practice. Like honestly, the web work homework is a little on the short side for the amount you should probably practice. All right, so this example is being explicitly written with y in terms of u, and then u, the g of x function, being defined to the side. So this one, we can split it up. It's already set up for our dy du and du dx format. So we look at our derivative of 5u minus 8. So 5 thing, the derivative of 5 times thing to the first would be 5 times 1 u to the 0. And then minus 8, the derivative of a constant, is 0. So our dy du is 5. And then our du dx, we're going to take the derivative of the inside function. So the inside function has a constant, so I'll just rewrite the 6/5 times the derivative of x to the 6th. I bring the power down, 6x to the 5th. So this is 36 over 5, x to the 5th. So dy du is 5, and then du dx is the 36/5 x to the 5th. And then if I clean this up, the 5's cancel out. So I just end up with 36x to the 5th. Now, if I recomposed the functions at the beginning, instead of using the format they gave me, so f of u would be f of 6/5 x to the 6th. So 5 times 6/5 x to the 6th minus 8. gives us 6x to the 6th minus 8. And then that's just a straight up power rule. Bring the 6 down so we get 36x to the 5th. And then the derivative of the 8 is 0. So there's our same 36x to the 5th. So questions on this one or anything else so far? All right, so our next one, we're going to have a chain rule inside a chain rule. So this one's going to look really silly. So when we're looking at this structurally, like here, the parentheses very nicely indicate outside versus inside to us. So when we go to do the derivative here, f prime of x, the first thing we do is the derivative of the outside, but keep the inside the same. So the derivative of sine of ugly is cosine of ugly. Then we do times the derivative of the inside. So the derivative of the inside is now the derivative of the cosine. Derivative of cosine is negative sine of thing. And now we do the derivative of that inside. So the derivative of tangent is secant squared. Now, because of the way the composition works here, like I would not try to simplify this at all. There's not any good like terms. It's all just a convoluted mess. You would never actually see a problem where you have trig function inside trig function inside trig function. Like we don't actually do that setup. But this is more an example of how the chain rule can work while also practicing our trig derivatives. All right, so this next example, we have a product rule, and then inside the product rule, we're going to have a chain rule. So I have x to the 8th times secant of thing. So there's my A and my B. So remember our derivative of the product rule. Derivative of A times B is A prime B plus B prime A. Like whichever way you want to write it, as long as you have derivative of one thing times original of the other plus derivative of other times original of the first thing. Right, so I use my differential notation just to like practice the product rule. Derivative of one thing times original of other plus derivative of other times original of first thing. Now, before we start doing the actual derivatives, the 1 over x to the 7th, I'm going to rewrite that as x to the negative 7th. That way, when we get to the derivative of the inside, it's a power rule instead of a quotient rule. All right, so our derivative of x to the 8th is 8x to the 7th. And now our derivative of the secant, we're going to have a product rule. So we do derivative of secant first, which is secant tangent. And then we're going to do times the derivative of the inside. The derivative of x to the negative 7th is negative 7x to the negative 7 minus 1 is negative 8. Now there is actually a little bit of nice interaction here at the end. The x to the negative 8th times x to the 8th. We'd add those powers. So negative 8 plus 8 is 0. X to the 0 is 1. So it's negative 7 times 1. So that means the second part can be written as negative 7 secant thing, tangent thing. The first part, though, like that's all she wrote. This x to the 7th is outside. The x to the negative 7th is inside the secant, so those two can't interact. So that one stays the same. So we took it a little slow, practicing our product rule, doing the more convoluted setup. But as you get more used to doing these derivatives, you won't have to write as many of the in-between steps. Now on the test, if you stopped, at that step, that would be perfectly fine. Like, especially when you just dealt with a disgusting product rule or a quotient rule, you don't have to clean it up. I only cleaned it up here because we actually had some cancellation happening. So it was just more of a like, oh, look, something canceled. Okay, so last chain rule here. This initial setup is a quotient. And we could work this as a quotient rule, but notice the top of this fraction is just a constant. And constants, you can just pull out of the derivative and just keep doing your derivative. So I can rewrite this to not have to do a quotient rule. Now, the other thing to notice, and it's kind of hard to see, but there is a negative sign in front of the fraction. So that is negative 64. And then my ugly mess on the bottom is being raised to a power. So I'm going to rewrite it as ugly mess to the negative second power. So I'm doing all this preemptively just because my brain is like, we're going to have to do a derivative. But let's actually read the question. So given the function and x sub 0 equals 25/4, find the equation of the line tangent to the curve at x equals x sub 0. So to find the equation of the line tangent to the curve, I need the slope and I need the point. So I have the x value. The derivative is going to get me the slope. But I need to know what this thing works out to be with my x sub 0 point value. So I need to know what r of 25/4 is. So once you have that all written, that is all a calculation. You could type that whole thing on the calculator. I'm going to run through it just because I'm used to doing this crap by hand. So the 4's cancel. So I have negative 25 plus 9 inside the parentheses there. So negative 25 plus 9 is negative 16. But then that's negative 16 squared. So I have negative 64 over 256. And it turns out 64 goes into 256 4 times. So this is actually negative 1/4. So I have my point for finding the equation of the tangent line. Now I need to find the slope of the tangent line. So slope means the derivative. So my negative 64 is a constant, so I'll just rewrite it. Negative 64 times. Now my derivative of the negative 4x plus 9 being raised to the negative second, I'm going to do the power rule on the outside first. So it'll be negative 2, my thing, negative 4x plus 9, raised to the negative 2 minus 1 is the negative 3 power. And then times the derivative of the inside, negative 4x plus 9 would be negative 4, 1x to the 0 is just times 1, so negative 4, plus the derivative of 9 is 0. So you could just write negative 4 there if you're comfortable with your derivatives. So I have my derivative formula. I need to know what's the slope of the tangent line at the x value 25/4. So I'm going to substitute in 25/4 for x. Now I'm going to do a little bit of cleanup. So the negative 64 times negative 2 is positive 128. And then times negative 4 is going to be negative 512. And I only know that because that's just a really big power of 2. Now at this point, I'm just going to type that in. I don't want to think that hard. So negative 512 times open negative 4 times 25/4 plus 9, close that, raised to the negative 3 power. I get the decimal 0.125, which is the fraction 1/8. So that is our slope of the tangent line, 1/8. I got my general formula for the derivative and then plugged in the particular x value that I wanted to know the equation of the tangent line at. So there's my slope of the tangent line. I've got my point. So I'm just going to use point slope form. Y minus y1 equals m onto x minus x1. Y1 is negative 1/4. Our slope is 1/8. And then our x1 is 25/4. So there is the equation of the line tangent to the curve at the value 25/4. So now that we know the chain rule, we can actually, like there's quite a number of quotient rules that we can rewrite as a product rule that uses a chain rule by just taking whatever the bottom of the fraction is and writing it up top as a product to the negative 1 power. Now, doing that as a product chain rule can be awkward to look at, but either case is just plain ugly. Now, the next thing I included is the derivative of e to the x, because this shows up in the homework sum, and it's also like, this is one of our classic chain rule examples that will show up over and over again. So it turns out that the derivative of e to the x is e to the x. So it is a weird function whose derivative is itself. So the slope of the tangent line at a point is the function's value at that point. But this means whenever I'm doing a chain rule with e to the x, so the derivative of e to the ugly is e to the ugly times the derivative of ugly. So one of the common calculus jokes is, a wild function appears. It's e to the x, and it's like set up as a Pokemon battle. You try differentiate. It's not effective. So little quick example, y equals e to the ax, where a is any real number. Then the derivative of this is e to the x is e to the x, e to the ugly is e to the ugly, times the derivative of ugly. So a is just a constant. So constant times x to the first power, 1x to the 0. So this is just a. So we'll sometimes just rewrite this as a times e to the ax. So a lot of our notes before this next test is just learning the derivatives of different weird functions. So this is another one of the weird functions that shows up. So overall, all we learned in this section was just what the chain rule was, and then we added the derivative of e to the x. Now, if you notice, it did say section 3.9, so I'm giving you a preview of section 3.9 with the derivative of e to the x here. Now, again, we've got 3 sections to cover in 2 days, so I'm going to move from chain rule into our next section. So our next section is 3.7, which is the derivative of inverse functions. A weird thing. So our generic question here is, what do we know about inverse functions? So if I gave you a function and I asked you to find its inverse, do y'all remember what the algebraic process is for finding an inverse? Why are you saying 1 over the function? Like there's a reason behind it. I just want you to try to articulate it. So like what's the notation for an inverse function? So inverse functions are written as f inverse of xy. Sorry, f inverse of x. I don't know why I said y. Now, one of the big things is, though, that even though that's that negative 1 power, which we know if it's applied to an x, that means 1 over x. That is not what the notation means when it's applied to a function. So even though normally the negative 1 power means 1 over f of x, when we're talking about inverse functions, that is not the reciprocal. So if I have the function y equals x squared, let's add plus 3. I want to know what the inverse function is. So one of the things to remember about inverse functions is they undo a function. So right now, my function takes an x value, squares it, and adds 3, and that gets me to a y value. I want to figure out the function formula that undoes those steps. So I need to undo adding 3, and I need to undo squaring. And with the way the inverse works, I'm also going to have to do it in the reverse order. So the classic example we use here is, think of a function as putting on your socks and your shoes. So you put on your socks first, then you put your shoes on. But when you go to undo that process, what has to happen first when you're undoing putting on your socks and shoes? You got to take off your shoes before you can take off your socks. So I know it sounds silly, but when we look at this function here, it's like, oh, I square the thing and I add 3. So my inverse should be square rooting and subtracting 3. And we are going to see those pieces, but the order we see them in is also going to reverse. Now, the algebraic function for finding the inverse is swap the x and the y's. And then solve for y. So I'm going to minus my 3 first. So I have x minus 3 equals y squared. And then I square root. So my inverse equation, because this isn't technically a function now, because of the plus or minus, but I end up with a square root, like I thought, and a minus 3, but the minus 3 is inside the square root. So this inverse function subtracts 3 and then square roots that result. So inverse functions undo, and the process for finding the undo function is to swap x and y. So now we're going to think about this in the context of derivatives. And strangely enough, with derivatives, by swapping the x and y, we actually end up with a reciprocal. All right. So if I have my function f of x here, this is like half of a parabola. So I pick an arbitrary point and I look at the slope of the tangent line. So that slope of the tangent line is q over p, like the rise over the run. If I look at the inverse function and that same point, then my slope becomes a reflection across the line y equals x. So my rise becomes the run, my run becomes the rise, because my x's and my y's are swapping. So originally we drew the function and we drew the inverse function by reflecting it across the line y equals x. Then I picked this arbitrary point on the inverse function, which is an x value of a. And then, because I'm looking at the inverse function, I would write that as f inverse of a. And then I just sketched the tangent line and arbitrarily labeled the slope. So the slope of this is p over q. Now, when I reflect this point back across, my x and my y swap. and then my rise and my run swap. So when I look at the derivative of my inverse, that ends up being the derivative at the inverse of a value. But that derivative of the inverse of the value was Q over P. My actual derivative of the inverse function was P over Q. So I also need to do the reciprocal. So basically we have weird, crazy picture with 20 million things going on, but inside that picture, we can show that the derivative of the inverse function at a value is the reciprocal of the derivative of the original function times the inverse at the value, or not times, of the inverse at the value. So here's our initial question. So we've got our definition of finding the derivative of the inverse. And what we use this for is finding the derivative of the inverse trig functions. So inverse trig functions, we apply an inverse trig function to a ratio of two sides, and it tells us the angle that would produce that ratio. So there's a lot of times where we're going to have a function where we have to use inverse trig functions. Like this is a very highly applicable function. So we need to know, how do I do the derivative of this? Now, when I look at my inverse function, inverse sine of x, I'm defining my original function as sine of x. So if f of x is sine of x, then g of x, being the inverse, is inverse sine of x, or arc sine of x. So the first step is figuring out what the derivative of the original function was. The original function is sine of x. So our derivative of that is cosine of x. Then we nest the two together. So we have derivative function outside, inverse function inside. So derivative of original function was cosine. And then our inverse function is inside. And then they magically say, and poof, this equals that. That step is not immediately obvious. But once they've defined this f prime of g of x, then when they go to define the derivative of g prime of x, we end up with the reciprocal of that thing we found. So what we're going to break down next is how we went from cosine of inverse sine of x to this square rooty thing. So when I say the cosine of the inverse sine of x, inverse sine of x is a placeholder for an angle. So some angle has an inverse sine of x. So I wrote that as a little equation that we're going to use to navigate this. Now I'm going to apply sine to both sides of this equation. So I now have that the sine of theta is x. I'm going to sneak in an over 1 because sine of theta is a ratio of two sides of a triangle. Now back up top, the cosine of inverse sine of x can be rewritten as the cosine of theta. So I now know that the sine of theta is x. I want to know what's the cosine of theta. So I'm going to draw a right triangle. Put it in quadrant 1. So I diagonal side into quadrant 1, drop the vertical side back to the x-axis, and label my angle. The angle is always the one whose vertex is on the origin. So let's label the sides of our triangle. So we got hypotenuse over here on the diagonal. Opposite is the vertical side across from the angle. And then our leftover is the adjacent side. Now we got to remember what sine, cosine, and tangent are related to for the sides of the triangle. So if you had pre-cal with me, you know about the hippies. If you haven't, you get to learn about them now. So what most people remember here is SOHCAHTOA, which works unless you're really bad at spelling. I have had people totally misspell SOHCAHTOA and then get thoroughly lost on a problem. So another way to remember it is to have a sentence where you associate a word to every part of it. So some old hippie caught another hippie tripping on acid. So when we say some old hippie, sine is opposite over hypotenuse. So in my triangle, that means my opposite side is x and my hypotenuse is 1. So I have a label for 2 of the 3 sides of a right triangle. I can use the Pythagorean theorem to find the third side. So I'm going to call the adjacent side A, the opposite side is then B, and the hypotenuse is always C. So A squared plus B squared equals C squared. This is A is our unknown, so A squared plus B is X, and C is 1. So I have A squared plus X squared equals 1. I minus the X squared because we're trying to figure out what's an expression for A. That's what we want to know here. So A squared is 1 minus X squared. And then I would square root both sides. And we have our plus or minus conundrum, but we default assume we're in quadrant 1, so we go with the positive square root. So now our question before was really asking what's the cosine of our angle. Cosine is caught another hippie, A over H, adjacent over hypotenuse. Adjacent is the ugly square root we just found over the hypotenuse is 1. So our trig function of the inverse trig function of x for cosine and sine, inverse sine, was the square root of 1 minus x squared. And that is what they claimed the cosine of inverse sine of x was. They wrote the square root of 1 minus x squared. So our derivative of inverse sine back here is 1 over that weird composition, So it's 1 over the square root of 1 minus x squared. Now, we're not going to make you guys go through this process for all of the trig functions. You could, um, but the whole drawing the triangle here, we did learn about that in pre-cal. So we're seeing it show up here, but it really comes into play when later on you start getting the antiderivative of inverse trig functions. If you can construct a triangle with the sides labeled appropriately, you can figure out what the antiderivative is. So what we have next is all 6 of the disgusting inverse trig function derivatives. Now, this is where we draw the line on the test. Having you guys memorize this bullshit is a little too much. So, on the test, we will give you these 6 formulas. You don't have to memorize these because these formulas are just too convoluted. There's too many moving parts. You do need to know your trig functions because most of those are smaller, they're more straightforward. And as you do the homework, you should be using them enough that they start to become more familiar. So some of these inverse trig function derivatives have an absolute value of x in them. But one of the interesting things is some of them have a negative sign on top. And oh, look, it's all the ones that are the c functions. So even the pattern we saw with the trig functions, where whenever we did the derivative of a trig function that started with c, we got a negative sign. Same thing actually holds true here. And if you look at like pattern match, derivative of inverse sine and derivative of inverse cosine are identical except for that negative sign. Then our tangent and cotangent are identical except for the negative sign. And then the same for the secant and cosecant. Identical except for that negative sign. So when we actually focus on these later on, we're really only going to focus on inverse sine, inverse tangent, and inverse secant, because the other ones are the same thing just with a negative. So there's no reason to use the negatives when we could just factor the negative out and use the positives. All right. So now here, our weird example is if our function is inverse cosine of x to the 5th, then what's our derivative? So off to the side, we've got our formula for inverse cosine. But our function is in terms of an ugly. So another way to think about our derivative formulas is everywhere there's an x, I can treat that and think of that as a u. So when I learned calculus, I worked with a different textbook, but my textbook would go to the effort for every time we learned a new derivative, they'd write the derivative in terms of x, but then they'd also write the derivative in terms of u. Now, the in terms of u is just applying the chain rule. So the derivative of inverse cosine of ugly is -1 over square root of 1 minus ugly squared times the derivative of ugly. So ugly is that x to the fifth. So now I'm going to follow my pattern. So my derivative is -1 over square root of 1 minus things squared. We're going to fill in x to the fifth. And then we do times the derivative of x to the fifth, which is bring the power down 5x to the fourth. Now again, if you're typing it on WebWork, absolutely you can type that first line we got, but you can clean it up a little. And the only reason I recommend cleaning it up a little is when you get to Calculus 2, you're going to have to undo these kind of weird setups. So it helps to see what the cleaned up version is, because that's what your antiderivative is going to start looking like. So our ugly squared, x to the fifth squared, is x to the 10th inside the big ugly square root, the 1 minus. And then on top, the -1 times 5x to the fourth is -5x to the fourth. So we've got a square root with x to the 10th and then an x to the fourth on top. So it's a kind of weird interaction between the two powers there. So what questions do you guys have on how we used any of this? We used the definition of the derivative of inverse cosine, and then we also used our chain rule. All right, I think we can do this one. So we got our definition of secant over on the side there. Our definition of the derivative of the inverse secant of x, sorry. But then our function here, I'm going to rewrite it a little because that square root, that can actually be thought of as s squared minus 1 to the 1/2 power. So when I rewrite it as the 1/2 power, now I've got a chain rule that I can do for my derivative here. So now when I start working my derivative, the derivative of this square root thing is going to be 1/2, keep thing the same, to the 1/2 minus 1 is the -1/2 power. And now we do times the derivative of the inside, which is 2s. Then minus, because we had a minus between these two pieces. And now our derivative of inverse secant of s. So we go over here to our weird form, 1 over absolute value of s times the square root of s squared minus 1. Now we have found the derivative. We could stop there. I'm only going to clean it up a little just so you can see structurally, these are actually kind of similar and yet also kind of different. So that is 2s on top. Well, I mean, really that 2 is going to cancel with the 1/2. So it's just s on top. And then that s squared to the -1 to the s squared minus 1 to the -1/2. I can move it on the bottom and rewrite it as a square root. So s squared minus 1. And then minus 1 over absolute value of s times the square root of s squared minus 1. So we can have weird setups where I have a square root thing and I do a derivative, and an inverse trig thing and do the derivative, and then the two pieces are very similar. Not completely, like the denominators are just slightly different. But if we needed to, we could common denominator and get these together. And then we would actually have something on top that's similar to the square root on the bottom. So weird stuff can happen. All right. Real quick, I'm just going to scroll to see. Oh, it was just one more example. Cool. We can do that one more example next time. And then what we're going to move to from there is what's called implicit differentiation. And we've actually already started to look at this with our dy du, du dx notation. Implicit really makes use of that differential notation. So yay, I don't have to record a video tonight. I am in the process of grading y'all's tests. I will have the tests to hand back on Thursday. I apologize for it taking so long. Making a ridiculous cake took way more effort than I thought it would. So much effort.